Now that we have come to a right understanding of the mechanism of sampling, with and without replacement, and of measuring subpopulations, it is now time to test your understanding of these three concepts. Let us go back to an ancient and venerable idea in the game of chance, that of a playing card. Let's start with a standard pack of 52 playing cards. These cards come in 4 suits, traditionally called spades, hearts, diamonds, and clubs, each suit having 13 cards, usually showing the face values 2 through 10, and then the distinguished values Jack, Queen, King, and Ace. Right. The particulars of these numbers don't matter for our purposes. All that matters is that there are 4 distinguished suits and 13 cards per suit. So here is the first problem. Take 5 such packs of cards, arrange them on the table. Flip open the first card in each of the 5 stacks. How many distinct sequences of cards would you be able to say? Pause the lecture at this point while you figure this out. When you're ready, restart. Now that you're back, let's examine how we might analyze this problem. 5 packs placed in a row. Now this is equivalent to saying, let's take one pack of cards, shuffle it, create essentially a random sequence, and flip open the top and see what you get. Write that down. Put it back, shuffle it again, flip open the top card, see what you get. That is the second value write down. Do this 5 times. The second experiment I've given you is formally equivalent to the first experiment, where you had 5 distinguished packs and you open 1 card from each pack. Good, but once you understand that what we're really doing is specifying 1 out of 52 distinguished cards, and we're going to do it 5 times, you realize that what you have specified is an ordered sample of 5 elements where the elements can be repeated. It is possible to draw the same card again and again and again, albeit it is rather unlikely. All right, how many different ways? Of course, this is sampling with replacement, and therefore the answer is going to be 52 times 52 times 52 times 52 times 52, or 52 to the power of 5, and you see this huge number, about 380 million possibilities. Beautiful. Now, let's take a look at another version of this problem. Take a standard pack of cards, shuffle it, and distribute 1 card to each of 5 distinguished players. 1, 2, 3, 4, 5. How many different sequences can they get? Pause the lecture again, and when you are ready, restart. Now that you're back, let's consider the problem anew. We have a single pack of cards and 5 distinguished individuals. 1, 2, 3, 4, 5. We are distributing cards 1 per individual. It becomes immediately apparent that what we are specifying is an ordered sample of 5 cards, arranged by individual 1 through 5. And since we're using just 1 pack of cards, it becomes clear that no card can be repeated. Each individual gets a distinguished card. In other words, the number of such sequences corresponds to sampling without replacement, and therefore the number of possibilities is 52 to the 5 falling, and that, if we work it out, gives you something like 300 million. The difference between this case and the earlier case, when sampling was with replacement, is relatively modest. And a little introspection will convince us that this, in fact, is reasonable. When you have large populations, in this case 50, 52, and we are selecting a modest number in our sample, the chance of a replication should be small. And indeed it is. Now let's move on to the third problem. Read it, pause, try to do it, think about it, and when you're ready, resume the lecture. Now that you're back, let's go on to a more real setting. Let's go to the game of poker. Now, poker is a game of chance where individual players, at least in elementary versions of this game, get 5 cards from a pack. Now observe that once a player gets 5 cards, then she simply keeps them in her hand, and the particular order she keeps them does not matter. How many different poker hands are there? Again, pause the lecture, think about it, see if you can work your way through to a solution, and then restart the lecture. Okay, now you're back. When we think about this, we realize that we are specifying 5 cards out of a pack of 52. This constitutes a standard poker hand, but the order does not matter. In other words, we are choosing 5 from 52 cards. And of course, the answer inevitably is the binomial coefficient, 52 choose 5. Evaluate it, and you find there are approximately 3 million poker hands. Now consider that this is a vast number. This is immediately one of the reasons why poker continues to fascinate. It is not a game like tic-tac-toe, where you have so few alternatives that you very quickly understand all of them. In poker, you have a large number of possible alternatives. That makes the game interesting. But the number is a small fraction of how many ordered samples there are. The moment you look at subpopulations, you decrease numbers dramatically. Our next problem is that of bridge. Now, bridge is a card game that continues to be popular in the age of the internet because of its rich structure. The way bridge is played is with a standard pack of 52 cards. There are 4 protagonists or players. They are traditionally called North, South, East, and West. The pack of 52 cards is distributed 13 apiece to each of the 4 players, North, South, East, and West. Each distribution of cards to these 4 players is called a hand at bridge. How many distinguished deal of hands at bridge are there? Pause the lecture, and when you're ready, restart it. Well, now that you're back, let's see how we might analyze this. We should have a formal procedure and understanding of how we're going to analyze this to avoid the perils of overcounting and undercounting, Scylla and Charybdis. We want to avoid either extreme. So how do we go about doing this? Well, let's say we're going to start by specifying the cards that North has, followed by the cards that East has, followed by the cards that South has, followed by the cards that West has. Here's an understanding, a memorandum of understanding between us. We're going to specify cards in this particular sequence. Well, let's see. How many ways can you specify the 13 cards that North has? Now, remember, order does not matter. And therefore, North can have 52 choose 13 ways in which the hand for North can be specified, specifying a subpopulation of 13 cards out of 52. Very well, so we have 52 choose 13 ways of specifying North's hand. Having specified North's hand, we have 13 cards fewer in the deck. We have 39 cards remaining. Of those 39, East gets 13, and there are 39 choose 13 ways of specifying East's hand from the remaining cards. Now, once East's hand is specified, there are 26 cards remaining, and there are 26 choose 13 ways of specifying South's hand from the remaining cards, which leaves us with 13 cards, and there are exactly 13 choose 13, or one way of giving those 13 cards to West. Okay, multiplying the possibilities, independent possibilities multiply, we obtain the number of possible deal of hands at bridge is given by a product of binomial coefficients. 52 choose 13 times 39 choose 13 times 26 choose 13 times 13 choose 13. And this is a huge number. This number is approximately 5 times 10 to the power 28. 5 followed by 28 zeros. This is a magnificently large number. To put it in proper context, consider that the number of brain cells in all the creatures that have ever existed on Earth might be a number like something like, let's say, about 10 to the power 25, about 1,000 times less than this number. This explains in part the enduring popularity of bridge. There's a vast, finite, but vast number of bridge hands, so large that we are not going to exhaust all the possibilities before the solar system dissipates.